Hello, everyone. Welcome back to IBPM Live, where process meets technology, people, and culture. So, our next segment is really exciting. We're going to talk about technology, we're going to talk about strategy, we're going to talk about creating a model-based system for the enterprise. And we have one of the best when it comes to that. Kenn Hartman is the Senior Partner and Manager Director of DSA. Hello, Kenn. We're really glad to have you here. Yeah, DSA is a PLM and digital enterprise and consulting practice, and Kenn has more than 35 years of experience in engineering systems and process design and the development of global digital enterprise strategies. So real honor to have Kenn here. We went from Tel Aviv, Israel, now from to Cleveland, Ohio. And Kenn, it's awesome to have you here this morning, and we're very honored to have you share your expertise with us today.
Around the world in just a few minutes, huh? Very nice. Thank you, Jose. All right, good morning, everyone. Thank you for being here today. I am going to talk about deriving a measurable return on investment from implementation of a model-based enterprise. Let's see here, I'm having a little trouble. Just a moment. Okay. I apologize. I'm having a little trouble getting the presentation. There we go. All right. First, we're going to talk about the pillars of success for Industry 4.0. It's critical to understand that before you can move through digital enterprise and Industry 4.0, there's a substantial amount of foundational work that you have to do. What I'm going to be talking about today is primarily moving from 2D to 3D so that you can better enable not only the engineering organization, but better enable automation, digital automation through the 6 pillars of success in Industry 4.0. So the first pillar, increased uptime, reduction in defects, new product introduction, improved productivity, human interface, and energy consumption. Now, if you look at reduction in defects, improved productivity, and human interface, you have to have very high quality engineering data. Specifically today, we're talking about a technical data package that has all of the information in it required to enable a high first pass yield of the downstream dependent supply chain processes. So I'm going to talk today about how to get there. So we start with the first foundational capability. You have to have standards. You have to have modeling standards, PMI standards, ballooning standards, and when you're creating a bill of characteristics, you need to create a 3D machine readable bill of characteristics so that you can enable all the potential downstream automation. Getting the standards developed is the first task. Getting them in, making sure the organization understands them clearly is the next hard task, and a lot of organizations throw this into self-paced training, and that has not proven to work very well.
Also, and just real quick, this is Jose here. Your video feed got frozen, so what I would suggest you do is that just turn off your camera and go with audio without your video feed.
Okay. Thank you.
Thank you.
Let's go back up. All right, so institutionalizing the standards through extensive training, and then modifying your engineering change process, at least initially, in a manual way, so that there is a checklist of things that you look for when you're evaluating the release of a 3D model, is critical to make sure that your organization is adhering to the new standards. After that, you'll need data definitions. What a data definition is for a specific part family. An airfoil versus a gear, for example. What is all the information required to enable that high first pass yield of the downstream dependent supply chain processes? That's what a data definition is. That's all the information. It's a specification for your technical data package. So when you look across your part family, if you have 30 part families in your part family tree, you're going to have somewhere between 8 and 15 different data definitions. So for example, if we looked at an airfoil, you'd have a data definition for casting, and then you'd have a data definition for complex machining. So just for an airfoil, you would exploit 2 different data definitions as you move that part through those 2 critical stages of its manufacturing process. Once you've got your data definitions and your standards in place, then you can build some initial technical data packages, and you can do a walkthrough of metrology, manufacturing engineering, quality, tooling, procurement, manufacturing planning, and particularly with your outsourced manufacturers, your critical outsourced manufacturing base. Once that set of walkthroughs is executed, it will allow you to do 2 things. It will allow you to tune the standards and tune your data definitions and execute some early pilots. So for example, try to auto-gen a CMM code. Have some manufacturing engineers take technical data packages and drive manufacturing work instructions, and you'll see that it takes a lot less time for them to do that from a TDP than it did prior to you creating that data definition and building that work product for them. Okay. So establishing the flight procedures, there is a very high level picture here of the process. What is the core infrastructure that you have to build? So you have to have modeling standards. You're going to have to exploit PLM extensively. And you're going to have to add some technology very likely to PLM. You're going to want, you're going to need to exploit middleware for storing CAD clones. You're going to have to update your part management and part object model, its relationship management rules. You're going to have to modify your engineering release process to automatically trigger particular validations of the CAD data, and perhaps even do producibility validation of the CAD data. In an automated way, and then automatically generate the CAD derivatives, JT, STEP, 3D PDF, etc., and generate the technical data package at particular life cycle states or states of maturity through the part management process. So it's critical that you understand what the end-to-end infrastructure looks like. We're going to talk a little more detail about this. So if we take CAD data validation, and there really are 2 critical components once you have standards and data definitions derived. There's 2 critical, or I should say 3 critical capabilities you need to have. You need to have good data validation, good producibility validation. You have to be able to generate technical data packages, and all 3 of those things are going to require substantial modifications to your PLM application environment. When you're doing CAD data validation checks, it's important to remember a couple of things. There's some easy stuff to do, and that is to implement generic checks. So is a component missing? Do you have a duplicate assembly? Is there a blocked hole? Do you have a void in the model? Those are generic CAD data validation checks that will work across all part families. Then you have to put in, as you move through multiple phases of increasing the sophistication of your CAD data validation process, you have to move to part-specific checks. So if you have a complex machine part that requires a tolerance of plus or minus 3,000s, you'll have to configure a tolerance check for that part family at that tolerance. If you have a small non-complex machine part that is plus or minus 10,000s, you'll have to make a copy of that same tolerance check and save it out so that you can run it against that particular part family that it's related to. So in order to do that, you have to make some pretty substantial PLM extensions. You have to define a part family tree, update your classification schema to enable people to classify each part into a part family. The engineering change process is going to read that value and be able to determine what set of checks you run on that particular part family and what data definition you use to produce a technical data package. You'll have to deploy a dispatcher. You'll have to deploy cloning tools. And you'll need to eventually update the ECO process to enable some deciphering of the validation reports that you get, such that if something is a tolerance check, for example, is critical and your tolerance check fails that, or your validation process fails that tolerance check, then you need to be able to automatically stop the change process and notify the change owner, for example. So as you move through this, the requirements for exploitation of PLM get more and more extensive. Very similarly, if we look at technical data publishing, you have to specify the data definitions across a family tree, specify the carousel views to be placed in each technical data package by part family. They will vary. The specific views the downstream supply chain requires for a given part family can vary. Every CAD system provides about 100 different views, so you just have to pick the views most relative to each part family. Then you have to drive a template for each data definition. That's the form, basically. And then you have to derive recipes to move data from PLM, ERP, and perhaps other systems into that technical data package. Now, the interesting thing about those two things, a lot of people go out and buy a third-party application for technical data publishing when they have a sophisticated PLM environment. You don't have to buy a third-party technical data package. You have all the tools right in your PLM application to do this. So think of a template as nothing more than a form. In the average PLM system, you can create a complex form and validate that form in 3 to 4 days. And then the recipes, as they're called in those third-party technologies, are nothing more than data migration scripts, which you can write in your own PLM. So by building it in PLM, you don't incur all the capital costs for servers and for the software. The configuration cost is about the same. And then, of course, you're not maintaining another application environment through help desk support and regular updates, server maintenance, et cetera, et cetera, et cetera. So as you think about technical data publishing, think about doing it right in PLM and run a pilot. So that really talks about the critical infrastructure required to enable the model-based design environment. Model-based design environment is critical to enabling the model-based enterprise. In the model-based enterprise, we will do things like automatically generate CMM code, do intelligent first article inspection, increase the or reduce the amount of time substantially to drive manufacturing work instructions, et cetera, et cetera. So as we look across the entire set of available ROI for model-based design environment and model-based enterprise, there are about 100 points plus or minus of value proposition for any given company. Over the last 3 years, we've been working with a number of organizations in automotive and aerospace who are well down the road on this environment, and we have a very sophisticated group of companies that come together on a quarterly basis and assemble return on investment metrics. So we have a substantial evidentiary library on ROI for model-based design and for model-based enterprise. And all of those companies are also reporting the critical capabilities that they had to put in, process and application capabilities to achieve the ROI. So any of you that would like to have that kind of detail about how to move forward, please feel free to reach out. I'd like to talk now, before we wrap it up a little bit, about ROI. So I'm going to provide some case studies here. So case study 1, jet engine manufacturer, 6 new engine programs a year, average of 2,000 parts per program. The average number of drawing sheets per part was 5. The average time to validate each sheet was 3.3 hours, fully burdened rate at $120 an hour. So the annual validation time, should now the dollar sign there, was 40,000 hours plus or minus at an average annual cost of $4.8 million. After we put in automated validation, and it was both generic checks and part family specific checks across 32 different part families, we achieved a real measurable reduction, cost savings of $1.7+ million, which was a productivity gain of 7.2 man years. And so the company was able to take all 7 of those people out of product validation and deploy them on new projects to do real engineering work, to do systems engineering work, requirements work, and CAD design work. So you can, even though they kept those employees, they did achieve a $1.7 million annual reduction in the cost to validate CAD. Real measurable money in the bank for that particular process requirement. Next example, average annual engineering quality notifications to have from suppliers to get the model to match the drawing that the automotive OEM was sending. So there was an average total hours to remediate end-to-end was 4 hours and 35 minutes. They did 374 of these on average per year. I'm sorry, back up. And it cost them 3,200 hours and lost engineering CAD designer productivity. That's 1.5 man years at a cost of $500,000 a year. So, boy, that keeps changing. I got to take the time off. The average annual EQNs 6 months after we put model-based design environment in was 11. So they substantially reduced that waste. So that was an increase in productivity. Next 2 examples. This is producibility. So we have 12,000 parts per year, 13% are built in-house, and that's 1,560 work instructions per year. The average time to derive and review and release a work instruction before technical data package was available was 22 hours. The average amount of time it took to create, review, and validate a manufacturing work instruction after TDP was 9.5 hours at an average annual savings of $2.4 million. In this particular case, this organization laid off 8 manufacturing engineers and put that money in the bank. So that in this particular case, high-tech manufacturer, they actually were able to achieve a staff reduction and still reduce the cycle time to release of a manufacturing work instruction. And by the way, the yield went up significantly. So we did not get, I think they reduced the number of returns to manufacturing engineering of a work instruction that was incorrect by more than 90%. Automotive OEM, subjecting parts to producibility review. They're plus or minus 6,300 parts subjected annually in this one case. This was for one product line, by the way. The average total hours executed producibility review was about 2.5. The total annual manufacturing engineering work hours was 15,000 hours at an average annual cost of $1.7 million. Once again, this was a situation where we were actually able to make a staff reduction of manufacturing engineers and achieve, in this case, about a $900,000 real savings money in the bank. So as you then look across product design, manufacturing, tooling, engineering, you might want to grab a screenshot of this, because these are some of the other areas where you can achieve ROI. And once again, if you want evidentiary ROI, you want to know what real clients have gotten for each one of these things, reach out. If you want to know what's how to calculate it, reach out. If you want to know what critical process and application capability is required, reach out. Quality, procurement, outsource manufacturing. Probably want to get a picture of this as well. Now, the big takeaway from this slide is if you have a very large outsourced manufacturing base, you're going to want to know what their model-based enterprise maturity level is. What is their capability maturity level? So when we survey outsourced manufacturers for our clients, we're able to determine what clients are immediately ready to consume a 3D technical data package and provide a return on investment back to our client. If you don't do this, if you just send the TDPs out to the outsourced manufacturers and don't put a process in place for getting the ROI back to them, you're going to leave a lot of money on the table. So you have to understand the maturity. For all those critical suppliers, it's 80-20, 20% are critical. Have a maturation plan for them, and then understand from internal data and from evidentiary data what ROI you should expect for every point of ROI there is, and look at the history you have with that outsourced manufacturer. If they're billing you 26 hours to create a work instruction, and you know it takes you 11 hours, you should be ready to negotiate what they're going to charge you from now on average to drive a manufacturing work instruction, so that you can see a line itemized reduction in your cost per unit engineered and manufactured by your outsourced manufacturing team. So finally, the last thing, because this is so complex, this is a project that is as large as implementing PLM, for example. Putting in model-based design and model-based enterprise is that large an initiative. You are going to need to execute it in stages. You are going to need to execute a strategic road mapping exercise. This is a good picture to snapshot, because it tells you what all of the critical work products are that you have to put in place. And also don't forget then that your model-based design and your model-based enterprise roadmaps are part of a much larger set of chapters in the overall Industry 4.0 strategic roadmap. So, call to action: derive a comprehensive strategic plan roadmap and get busy with the foundational work, and do it. And you can do that while you're doing the roadmap, by the way. Don't skip on standards training, assure institutionalization, and then make sure you design and build this thing for real ROI. Know where the ROI is and know how to get it. That's all for my presentation. If you screen capture this and want to reach out, now's a good time to do that. And I think I'm supposed to stop sharing my screen.
Yes, Ken, because your video feed is not transmitting very cleanly. I'm gonna ask you to, in this case, share your presentation and go back to that page where you had the strategic roadmap, if you will, where you have the big picture on your presentation. And
very good.
That one right there. That one right there. And I will. There are questions that are coming in from the audience here. I'll turn my camera on. You may want to try to turn your camera on just to see if your video feed may have gotten improved at this point. Give it a shot. And if that's not there, don't worry about it. It's not critical. That would be on the interface of the
It's
go-to webinar.
it's not coming on.
Yeah, so let's leave it off so that it doesn't impact. Your audio is very clean, so I'll just ask you the questions. And I think that the reason I ask you to put that strategy map back there is because it provides the context for a number of questions that I have seen coming up. So for those of you who are listening in and watching this, keep providing your questions. Okay, I'll get to them as you provide the questions and insights. So the first question is that it was, as a matter of fact, there was a comment that was funny because there was a page where you show that the initial part of the journey, and there was an incredibly complex diagram of the steps that to be taken, and then you said we're gonna get into the details of that, which was awesome because it's like that is the high level, folks, because this stuff is hard. So I want you to talk to us a little bit about this, and we appreciate the expertise that you have, because to simplify, you must master complexity, and this is not necessarily a simple thing to do. It's a complex process, and it's in mastering that complexity that you can come up with simplifications. But there is no obvious, trivial solutions for some of this challenges. So the first question is on that, on how do you even start this journey in an organization that may not have, thought deeply about all these interconnections. So how do you work with an organization that's just getting started?
Yes, so the first and most critical task is executive education and executive development. So what we would typically do is we would come in to a client site and we would sit with the team, the engineering community, and some of the operational folks, and we would provide some initial project plans, some outlines of roadmap, and we would work together to derive an executive level deck to educate the executive team on what the real ROI is available for this. How should they get started? What resources will they initially need, et cetera, et cetera. So we offer a 2-week readiness preparation activity that we do for clients on nickel. So we'll work with them to put all that initial information together so that they can take it to the executive team and have that built in to their strategic digital enterprise roadmap. So that's the first thing to do. Once the executive staff gets on board, you can start ferreting out all the rest of this detail for the entire journey. And while that's going on, you start the derivation of standards and data definitions. And that's how you get started.
And the next question that we had here had to do with, and you gave several awesome examples on how you apply and how you derive the ROI from these applications. But if you look across all your clients, the opportunities that you see in the industries that often go beyond what even your clients can see themselves because they have limited understanding of the capabilities. Where do you see the best applications for model-based enterprises across different industries? Where is there certain industries or certain applications that stand out?
Well, certainly if you're looking at heavy equipment, aerospace, automotive, engineering, procurement, and construction, where they're building, so, for example, if you're building power plants, you have turbines, you have bag houses, you have, a number of things that are standard products that you develop. It's a very good application for those things. In the high-tech industry, there is good ROI, but it's a little less than it is for a hard mechanical manufacturing provider. Then, of course, if you look at an organization that, for example, does their product is primarily mold injection. So, for example, an organization like Adient that makes automotive interiors. We still don't. We are still not able to derive really good ROI from an organization that is largely a mold injection firm. But if you're an automotive OEM, tier 1, tier 2, tier 3 supplier of mechanical parts, you can make a lot of money with model-based design and model-based enterprise. If you're in aerospace, you are already marching down this path. Northrop Grumman, for example, has allocated more than $100 million to move into model-based design and model-based enterprise. Lockheed has almost matched that amount of money. Pratt Whitney has already spent $15 million perhaps on this program. So aerospace is really far ahead, but large mechanical manufacturing firms or electromechanical manufacturing firms can achieve a substantial ROI.
So that's very, very helpful. Another question that came up is a little bit on the perspective on the model-based design environment industry, a little bit of a history on it and how it has evolved to where it is today. Any thoughts that you can share a bit on the history of this discipline?
Yeah, so a number of years ago, the United States Air Force actually was the first DoD organization to really start looking at the opportunities available for them to drive their supply base to 3D. And so there were some consortiums that were put together. Very shortly after that, the Air Force went out to the National Institutes of Standards and began to develop a group at NIST. And there are, by the way, several committees at NIST, one on standards, one that's deriving, modifying ASME standards. There's a committee for MIL Standard 3000, A and B, which is PMI standards. And then at DMSC today, there's now a group of guys that are taking a look at how to create a machine readable bill of characteristics. So as the Air Force started to evolve, they started to notify their manufacturing base, their suppliers, that at some point in the future that they were going to make as part of their contract a requirement that they be provided a full three-dimensional technical data package. So the aerospace industry started taking an early look at it, and as they started running pilots, they started to realize how very complex the program was and how very long it was going to take them to fully transition their entire corporation. So they started in earnest, the aerospace industry, about 3 years ago, really started going fast. And just on the heels of that, General Motors, Chrysler, Ford, BMW, et cetera, also started large projects and started pushing their supply base, tier 1, 2, and 3, to drive to model-based enterprise as well. So those are the industries that are currently leading the charge and making progress. And then, of course, over the last 3 years, we've seen a number of organizations come in to play to provide third-party software applications. So producibility validation, CAD data validation, derivative validation, translation technologies, and technical data publishing tools. We've also seen organizations produce things like intelligent FAI capabilities. So you can take the data right off the CMM and pose it right back onto the model, so you can see your issues color-coded and annotated, and be able to move through the FAI process much more effectively and much more efficiently.
Very good. One other question that we have here is around the concept of digital twins, and the question is
Yes,
whether how this that's kind of this 3D model approach that you have here may marry or support this concept of digital twins. Is that something you're familiar with?
absolutely, yes. So some people are suggesting that a two-dimensional drawing of a part and then the physical part are digital twins. They're not. A three-dimensional model that has machine readable bills of characteristics, intelligent ballooning, and those kinds of things, that is what a digital twin is. So let's for example take a look at a smart factory with intelligent robots and machines that all talk to one another as a product is moving through a manufacturing process. And that's where we're headed, by the way. Organizations like Rockwell have committed Rockwell committed last year to spend more than $3.5 billion to drive smart factories. So if you have a smart factory and your machines and your robots are going to talk to one another and make autonomous decisions, they're not going to be able to read a two-dimensional drawing. It's just text. So you have to, as you start to move through all of those pillars of success for Industry 4.0, you have to understand that creation of the digital twin means the physical part and an intelligent digital representation of the part. And that's critical, an intelligent digital representation of the part.
That's incredible. Just the vision that you're sharing there and the a full automation approach with a digital twin. It's quite impressive. The last question that I have here is related to advanced technologies, and you may have partially answered this already, but just to confirm, how do you see the play of AI, RPA, machine learning, this new not new, but this exponential technologies that are becoming more dominant currently, playing with these concepts that you're talking about here?
Well, so for RPI, I've kind of described that a little bit in the last question. Let's take something else that it's emerging that will be part of a smart factory. Let's take 3D printing. So when you look at 3D printing today, you have to, of course, you have to have a three-dimensional model. You can't do 3D printing with a two-dimensional model. And in particular, when you are designing 3D parts, you need to design 3D parts using a lattice structure, which we could never do before. We could never build a part with a lattice structure because I can't take a raw piece of metal and make that raw piece of iron have a lattice structure. So we can only do that with 3D printing. So today, you have to apply generative design techniques, lattice structure, and then you change how you do real-time simulation of those models so that you can create a three-dimensional model. And once again, a machine-readable bill of characteristics is also required so that you can feed that model directly into the 3D printer. The 3D printer will generate its own code automatically and then be able to derive that lattice structured part. So for those of you who might not understand what I mean by lattice structure, the simplest example is if you think about a woodpecker's beak and his ability to pound on an oak tree and not break it. The reason that is because the interior of his beak is very much like a honeycomb. It's a lattice structure, and it makes it much stronger and much lighter.
Fascinating, Ken. Fascinating. Thank you so much for sharing your expertise with all of us today. Incredible journey, complexity, value, the drive for innovation and value creation, all very clearly represented. Thank you so much for sharing your expertise and insights with us.
Thank you so much, Jose, and thank you everyone for attending. Y'all have a great day.
Thank you. Ladies and gentlemen, this completes our session, and in fact, this will be the last segment that I'll be able to facilitate today. And but you will be in the very capable hands of Brian Raffel and this beautiful British voice that will guide you through the rest of the sessions. So thank you for joining us. Make sure that you provide feedback on the session as you exit this segment, and log back on for the top of the hour. And we'll carry on the discussion on how business process management marries technology, people, process, culture. Thank you very much.